In this lecture, we will review the concept of Fourier theory or Fourier analysis, and that is something that you must have studied in your undergrad degree, but I will nonetheless give a quick review of Fourier because a lot of concepts from the Fourier analysis would be used in our discussion in the subsequent topics and even in in future lectures as well. So the first thing we're going to do today is a quick review of Fourier analysis. I've also given you a tutorial sheet which contains problems related to Fourier transforms and the properties of Fourier transform. Okay, so you need to complete that tutorial sheet so that you have a clear understanding of what happens in Fourier transform and what are some important properties of Fourier transformations. Okay, so you'll complete that tutorial sheet, and nonetheless I'll give you a quick overview in the first half of the first part of today's lecture. And then much of the focus of today's lecture is going to be on discussing what are referred to as low pass signals and what are referred to as band pass signals, and then how to represent band pass signals in the form of low pass signals. So how do we transform or represent a band pass signal as a low pass signal? Okay, and the reason we would do that is because a band pass signal basically means the signals are represented at some higher frequency value, and we want to bring them back towards the lower frequency value. So how do we represent the signals which are centered along some high frequency onto in terms of low frequencies? Okay, so that makes the analysis or the design of systems much easier. It makes the processing of low frequencies much easier than processing higher frequencies. So there is a need to represent band pass signals, which are basically signals which are centered on some high frequency in terms of lower frequencies. So that is what we call as the low pass representation of band pass signals. Okay, and that is what we're going to do. So let's begin with the basic expression for the Fourier transform. So the Fourier transform is equation is given as let me write that a bit clearly. Fourier. Now, when I say Fourier transform, depending on the type of the signal, it could be Fourier transform of Fourier series. Okay, for example, if you're dealing with a periodic signal, that would mean Fourier series. But if it's a non-periodic signal, it could involve Fourier transform. But in general, we'll simply call it as Fourier transform. Okay, and deal with it as in the form of a transform itself. So the expression for the Fourier transform is x of f is equal to integral minus infinity to infinity x of t e power minus j 2 pi ft dt. Okay, so where x of t is the time domain signal and x of f is the Fourier transform of x of t. Okay, so x of f is the frequency domain representation, x of f is the Fourier transform of the signal x of t. So x of f is the Fourier transform of x of t. Okay, and by using this expression, we are going to quickly review the Fourier transform of two basic signals, one complex signal and one real signal, and then we'll see what is the distinction in their spectra, that is. Okay, and then we will use those properties in our analysis. Okay, so let's start with the Fourier transform of x of t equals e power j 2 pi f naught t. So that's a complex exponential signal with some frequency f0 or f naught. Okay, so we want to evaluate the Fourier transform. So it's the general expression is x of t e power minus j 2 pi ft, but in place of x of t we have e power j 2 pi f naught t, so we substitute that, and then we're combining the two exponentials, we get e power minus j 2 pi f minus f naught t dt. integrated from minus infinity to infinity, and that integral is basically equal to delta of f minus f naught. And how that comes is because since, let me write that, since integral e power, let me write that a bit bigger, integral of from minus infinity to infinity e power minus j 2 pi ft dt is equal to delta of f. So that's the standard relationship. So I'll put that in a square. So using that relationship, in place of f here, we have f minus f naught. So when it's integral e power minus j 2 pi ft dt, we have delta of f. In place of f, we have f minus f naught here. So that's the only difference between these two expressions. So instead of delta of f, it becomes delta of f minus f naught. So the argument here is f minus f naught instead of f. So the right hand side, instead of delta of f, is now delta of f minus f naught. Okay, and that's basically the Fourier transform of this complex exponential. That's the mathematical thing, but basically what you're saying is the Fourier transform of this complex exponential, which is e power j 2 pi f naught t, which can be x of t equals e power j 2 pi f naught t, which is nothing but cosine 2 pi f naught t plus j sine 2 pi f naught t. So basically that's a complex signal, right? It has a real part and it has an imaginary part. So it's a plus j times b. So that's a real part of the complex signal and the imaginary part of the complex signal. And what we notice here is that the real part is cosine and the imaginary part is sine. So that means the imaginary part is a 90 degrees shifted version of the real part. So sine is 90 degrees shifted from cosine, right? So the imaginary part of this complex signal is 90 degrees shifted version of the real part. Now, the Fourier transform of this complex signal is given by delta of f minus f naught. Delta of f minus f naught is nothing but, delta means an impulse function, and it's a shifted impulse in the frequency domain, right? So it's an impulse in the frequency domain at a frequency f naught. So if we had to plot this, we'll get it something like this. So that's going to be along the frequency axis, right? And we are plotting x of f along the y-axis. So that's x of f, and on the x-axis we have the frequencies. So basically that's an impulse function at f equal to f naught. So it's an impulse shifted to the right by f naught. So we have an impulse like this here. So at f naught, all right, so that's an impulse at f naught. Exactly, so that's the value f naught. So basically what we notice is it's an impulse at only f naught, because that's the frequency present in that signal. So basically what the Fourier transform tells us is, it tells us what frequency components are present in the signal and what is the amplitude of that frequency component. So at f naught we have an impulse of height 1, because the amplitude here is 1. So this height here is 1. So if the amplitude was 5, then the height of this impulse would be 5. If it was 2, then the height would be 2. But the important thing to notice here is that when we have a signal which is a complex signal, okay, then we see that the spectrum or the Fourier transform of the complex signal is one-sided, which means that it has an impulse only on the positive frequency axis. There's nothing on the negative frequency side, right? So to the left of 0, there is no impulse, right? And that's the distinction that we're going to see when we deal with real signals rather than complex signals. If we have only real signal without the imaginary part, then we will see that the Fourier transform will come out in such a way that there is a frequency component and the positive frequency axis, as well as on the negative frequency side. Okay, so that means the spectrum will be two-sided for the real case. For the complex signal, the spectrum is one-sided. So this x of t that we have here is given for complex signals. The spectrum x of f is what we call as one-sided. Okay, so that means it is only on one side of the frequency axis. It is not available on the other side. And next we will do an example for a real signal of some frequency f naught. So now we have seen it as a complex signal which has a real part and an imaginary part. But now we will see a real signal which has no imaginary part. So we take the x of t as simply cosine 2 pi f naught t, and we will compute its Fourier transform. So again, the general definition of the Fourier transform is x of f is equal to integral minus infinity to infinity x of t e power minus j 2 pi ft dt, which is equal to x of t is our cosine 2 pi f naught t now. So that's minus infinity to infinity cosine 2 pi f naught t into e power minus j 2 pi ft dt. And we are going to use Euler's relation to represent cosine 2 pi f naught t in terms of a complex exponential. Okay, so since cosine 2 pi f naught t is equal to e power j 2 pi f naught t, j 2 pi f naught t plus e power minus j 2 pi f naught t divided by 2. So we're going to use this relationship. So I'm basically going to write that divided by 2, I'll take it as a common factor here. So we have this representation for cosine, right? So we're going to substitute this relationship into here. So that will make our Fourier transform x of f as half integral e power j 2 pi f naught t into e power minus j 2 pi ft dt plus half integral e power minus j 2 pi f naught t into e power minus j into e power minus j 2 pi ft dt, right? And that integral goes from minus infinity to infinity, and similarly here. Okay, that's the limits of integration. And basically now we can write that as half integral minus infinity to infinity e power minus j 2 pi f minus f naught t dt plus half integral e power minus j 2 pi f plus f naught t dt, right? And once you have it in this form, we see that this integral is simply going to be delta of f minus f naught, and this integral is going to be delta of f plus f naught from our previous relationship here, because you see here integral e power minus j 2 pi ft is delta of f. So instead of f we have f minus f naught and f plus f naught in our terms here. So instead of f we have f minus f naught, and here we have f plus f naught. So that becomes delta of f minus f naught. So that means that entire integral becomes delta of f minus f naught, and this integral becomes delta of f plus f naught. So that becomes half delta of f minus f naught plus half delta of f plus f naught. So now when we plot the spectrum for this, then you will see that it is indeed a two-sided spectrum. So let's plot that. So we have x of f equals half delta of f minus f naught plus half delta of f plus f naught. So when we plot this, we're going to have the spectrum as a two-sided spectrum. So that's our frequency axis f. So, and on the y-axis we will have x of f. Now, what's our zero frequency point? That's the origin basically. And what we see is this spectrum x of f that's an impulse delta of f shifted to the right by f naught. So delta of f minus f naught means f minus means right shift by f naught, and plus means left shift by f naught. So that's an impulse at f naught, and that's an impulse at minus f naught. So we can make those impulses. So at f naught we have an impulse, and symmetrically on the opposite side at minus f naught we will have another impulse. So that's our spectrum. So at f naught we have a frequency component, and at minus f naught also we have a frequency component. But now what you notice is the amplitude is half and half on each side. So both have an amplitude of half. So what we see is that when we are finding the Fourier transform or spectrum of a real signal, the frequency components, the spectrum has frequency components on both the positive side and the negative side, and the magnitude gets divided half to the positive side and half to the negative side, because the amplitude here was 1 for this x of t, and that 1 has got divided half on the positive side and half on the negative side. So the spectrum is now two-sided. Okay, and the reason for this negative frequency component arising in the spectrum in the Fourier transform is because we are trying to represent the a real signal as the sum of complex signals. Okay, so complex signal has a real part and imaginary part, but our signal is only a real signal. So we are trying to represent this real signal as an integration or summation of complex signals. So what happens is, to cancel out the imaginary part so that we get a real result, we have to add the complex conjugate to it. So when we add the complex conjugate, the imaginary parts will cancel out. So that's how the negative frequency component comes, because the complex conjugate is basically obtained by multiplying with the minus f here. So minus f corresponds to the negative frequency, and that's how this minus f part comes here. Okay, that's I'll allow that as an exercise for you to read in your own time. But the important thing that I need to highlight here is that for the complex signals, the spectrum is going to be one-sided, and for real signals, the spectrum will be two-sided. Okay, so the moment you see the spectrum, and if you notice that the spectrum is two-sided, that means the corresponding signal is a real signal. And if the spectrum is one-sided, then the corresponding signal is a complex signal. So and when we have a real signal, whatever is the amplitude, it gets divided half to the positive frequency side and half to the negative frequency side. So that's an important fact that I want you to notice. But nonetheless, negative frequencies do not exist in reality. There is no such thing as minus 10 hertz or minus 50 hertz, right? So it's a mathematical convenience that comes in the mathematical analysis tools. So we'll use it because it makes life easier, because it's much easier to deal with the exponential functions than with the cosine functions themselves. Okay, so the observation that we make here is that for real signals, the spectrum is two-sided. Okay, so that's an important observation. For complex signals, the spectrum is one-sided, as we have pointed out here, where we had a complex signal which is e power j 2 pi f naught t, and when we deal with a real signal cosine 2 pi f naught t, we get its Fourier transform is such that it has a positive frequency side as well as a negative frequency side. So the spectrum is two-sided for a real signal. And the next property that I want to highlight from the Fourier analysis is what is called as the modulation property, because modulation causes the spectrum to shift by a certain amount. Okay, so that's another property I want to review very quickly now. So that's because we are going to use that property in our analysis several times. So we call it as the modulation property of Fourier transform. Okay, and what it means is that let's say we have a signal which is centered on zero frequency. So I'm going to just mark a signal. So suppose this is our signal. This is the spectrum of a signal x of t. So x of f is spectrum of some signal x of t, which is a low pass signal. That means the spectrum is centered on zero frequency, right? So the central point is zero. So if we have the signal x of t multiplied with a real with another real signal like cosine 2 pi f naught t. So suppose you have x of t multiplied with cosine 2 pi f naught t in the time domain. What happens to the spectrum of this x of t as a result of this multiplication in the frequency domain? Now the Fourier transform for x of t is x of f, and the Fourier transform for cosine 2 pi f naught t, which we have seen earlier, is this delta of f minus f naught plus delta of f plus f naught, right? So basically multiplication in the time domain here corresponds to the convolution of their respective Fourier transforms. So that is basically in the frequency domain x of f convolved with let me make some space here. So in the frequency domain, that will be the Fourier transform of x of t convolved with the Fourier transform of cosine 2 pi f naught t, which is half delta of f minus f naught plus delta of f plus f naught. Okay, so it will be the convolution between these two signals, and as a result of this convolution, what we will get is this spectrum, which is centered on zero, will get shifted to the right by an amount f naught and also shifted to the left by an amount f naught, because we are dealing with a real signal here. So the spectrum of this signal after multiplication will be two-sided, because the carrier signal here is a real signal, right? So let's plot that. So what we see is that as a result of this convolution, the spectrum z of f of the signal z of t, which we obtain by multiplying the time domain signal x of t with cosine 2 pi f naught t, which we can call as a carrier signal, is basically the convolution of the respective Fourier transforms, and that is basically equal to z of f. Okay, if we denote that as z of f, it's basically half into x of f minus f naught plus half into x of f plus f naught. So we have a replica at f naught and another replica at minus f naught. So it is a two-sided spectrum, and basically what we see is that the signal which was centered on 0 as a result of multiplying with some frequency component f naught, where f naught is large, okay, the spectrum gets shifted by an amount f naught, okay, and we get a replica at minus f naught as well, and the replica arises because of the because the signal is real, and the Fourier analysis is trying to represent this real signal as a sum of complex signals. Okay, so we get this two-sided spectrum, and this is what we call as a modulation property. Modulation property basically says that when we multiply a signal with another signal of some frequency, the spectrum of this original signal gets shifted by an amount equal to the value of the frequency of the second signal that we multiply it with. Okay, so modulation produces frequency translation. The frequency, the center frequency gets translated to a new value f naught. From 0 it has got shifted to f naught. So modulation produces frequency translation, and to produce that frequency translation or modulation, we are basically multiplying the signal with a carrier signal of some frequency f naught. So what the observation that we make here is that modulation produces frequency translation. Okay, so as we see here, the original signal x of t, which had some spectrum x of f centered on 0, after that signal is multiplied with some real carrier signal of frequency f naught, then the resulting spectrum after that multiplication is a shifted version of the original spectrum, but it is also two-sided. We have a replica on the negative f naught as well, because this is a real signal. But if we had to multiply this x of t with a complex signal e power j 2 pi f naught t, then we would have only the positive frequency axis side. There won't be a component on the negative frequency side if this carrier was a complex carrier signal. Okay, but in real life we are going to deal with the real signals, but sometimes for the purpose of analysis we would use a complex signal just to make our life easier. Okay, it sounds counterintuitive that the complex signal actually makes the analysis easier, but it does indeed, because when you're dealing with complex exponentials, it is e power j something, right? And dealing with the exponentials is a lot easier when you're performing integration or differentiation. So that is why we use them as in our mathematical analysis. Okay, so that's our frequency axis f, and on the y-axis we had the z of f, which is a Fourier transform of z of t, which is given by this. So basically x of f minus f naught is a right shifted version of x of f, and x of f plus f naught is a left shifted version of x of f, which is here. Okay, and because of this half factor, if this whatever is the original amplitude in the spectrum, that gets divided half on the positive side and half on the negative side. So suppose if we had this as 1, then these peaks would correspond to half. Okay, if this was in the original point, if this was 5, then it would be 2.5 and 2.5. If this was 10, then it would be 5 and 5. So the magnitude gets divided half on the positive side and half on the negative side, because the power has to be, or energy has to be conserved, right? You can't, the signal has a certain power or energy depending on whether it's a power signal or an energy signal. Okay, so we are going to use this property a lot in the subsequent discussion that we're going to have today, where we will discuss about how to represent a bandpass signal in the form of a low-pass signal. So you need to have a clear understanding of these three particular points. The first is that When the signal is complex, the spectrum is going to be one-sided. When the signal is real, then the spectrum is going to be two-sided. And when you multiply a signal with another signal of some frequency, this is a monochromatic signal, that means it has a single frequency component, then this signal, which has many frequency components, we are multiplying it with another signal which is having a single frequency f0, then the spectrum of this product is basically the original signal spectrum shifted by a certain amount, f0, which is the frequency of the carrier signal that we are multiplying. And because this is a real carrier, we have a replica on the negative frequency axis as well. And basically what we see is here, by multiplying in such a with a carrier signal, we are able to translate the frequency or shift the spectrum of the original signal by a certain amount. So depending on how much we want to shift it or where we want to shift it, we can choose the value of f0 accordingly and have it shifted. And similarly, if you want to bring it back, so we can do the opposite action, so bring it back by multiplying with the corresponding carrier signal. So by using this modulation property, we can make the spectrum to shift either to the left or to the right, but according to our needs. And we will be using this property in our discussion. So next we will discuss what we mean by a low pass signal. Okay, so what is shown here is the spectrum of a low pass signal, and basically a low pass signal is a signal whose frequency components lie around 0 Hz. So this spectrum is centered on 0 Hz, or it need not necessarily be the central. The 0 Hz need not necessarily be the central value. But the signal in general has frequency components which are around 0 or near 0, or we call it in the vicinity of 0. So we can have this spectrum lying somewhere like this also. So but nonetheless, it is somewhere close to 0. Okay, so it's not necessary that the 0 is exactly in the center. It could be here or it could be here also. But in general, the low pass signal is a signal which has frequency components in the vicinity of 0 Hz. So low pass signal has frequency components, in the vicinity of 0 Hz. Okay, so that's what we call, or we refer to as a low pass signal. And sometimes we also call a low pass signal as a baseband signal as well. Okay, baseband signal. And we can define the bandwidth of the signal as the maximum frequency value that is present in the signal. So it starts from 0 and ends at some value which we call as W, and similarly on the negative side it will be a corresponding minus W. So a low pass signal is such that its spectrum is 0 outside W, right? So X of f equal to 0 for frequency values greater than W, or for frequency values less than minus W. So to the right of W and to the left of minus W, the frequency value or the spectral components are 0. Okay, they don't exist, right? So that is what we mean by a low pass signal. Or combining these two, we can simply write as the magnitude of f to be greater than W, right? So that is what we call as a low pass signal. So the equivalent way of writing that is basically x of f equal to 0. Equivalently, x of f equal to 0 if the magnitude of f is greater than W, and it is not equal to 0, non-zero if the magnitude of f is less than W. Okay, so between minus W and plus W, it has some non-zero frequency component values, and greater than W or less than minus W, that means when the magnitude of F is greater than W, the spectral values are 0. Okay, so that's an equivalent way of giving this expression. Okay, so that's for the low pass signal. Okay, next we will see what is a band pass signal, and then we will discuss a process of how to convert or represent a band pass signal in terms of a low pass signal. Okay, and what we'll see is that even with the real band pass signal, when we represent it as a low pass signal, the low pass representation of a band pass signal which is real will still be complex. So the low pass representation of a real band pass signal will be a complex signal. So when you convert a real band pass signal to a low pass equivalent, then the low pass equivalent, we will see that is going to be a complex signal. Okay, but we still do it because the analysis at lower frequencies and processing becomes much simpler as compared to processing the signal at higher frequencies. So in such cases, we need to translate the higher frequency band pass signal to a lower frequency low pass signal. And just to distinguish the spectra for when representing the low pass signal, I've used the subscript small l here. So it's XL of F to denote that this spectrum represents the low pass signal. And similarly, when denoting the band pass signal, I'll use the subscript B, XB of F, to represent that it is a band pass signal. So now we will define what we mean by a band pass signal. A band pass signal is a signal whose frequency content lies in the vicinity of some high frequency value F0. So rather than the frequency components being in the vicinity of 0 Hz, they are now in the vicinity of some frequency value F0, where F0 is generally a large value. So F0 is a high frequency value, and all the frequency content of the signal is in the vicinity or neighborhood of that high frequency value F0. So the definition for a band pass signal is that the spectrum of the band pass signal, which we denote as XB of F, contains frequency components which are in the vicinity of some high frequency F0. So as we said, a band pass signal is a signal whose spectrum contains frequency components which are in the vicinity of some high frequency F0. Okay, now this frequency F0 is usually referred to as the central frequency. F0 usually referred to as central frequency. Okay, now we have to be cautious about this term central frequency. It is usually called central frequency, but it is not necessary that F0 lies exactly in the middle of the spectral band of the signal. Okay, so it's as we will see shortly. So this F0 need not necessarily be in the center. It can be here, it can be here. In fact, it is not even necessary that this F0 lies within this band. It can be outside this band, but it should be near the band. Okay, so it is still called a central frequency, and generally we will keep it as a center, but it is not necessary that it lies at the center or even inside that range from F0 minus W to F0 plus W. It can be outside this range, somewhere here or even somewhere here as well. So we have to be, while we'll use the term central frequency for it, we need to remember that it does not necessarily be at the center of the spectral band. Okay, now the other definition that we will see here is the bandwidth of the signal. So we'll see that the bandwidth is now extending from this limit to this limit. Okay, bandwidth by definition is the range of all positive frequencies. So on the positive axis, it goes from it starts from this frequency point to this frequency point. So from F0, it is having a width of W to the right and another W to the left. So that bandwidth here is 2W. Okay, so for this particular signal, the bandwidth equals 2 times W. Okay, in contrast, for the low pass signal, we had the bandwidth which is this side only, because bandwidth by definition is the range of all positive frequencies. So the bandwidth here, bandwidth is equal to W hertz. Okay. Now we will see the case of the spectrum for the bandpass signal where the central frequency f0 is not exactly at the center. So I have depicted two plots here. So here in one of these we can have this f0 somewhere here, so it's not at the center, so we have somewhere like this. Okay, so that's our f0, and in the third case we'll just put this f0 outside the band itself. So that's also a valid band pass signal. Okay, so as I said earlier, this central frequency f0 need not be at the center or even inside the frequency band of the spectrum of the signal. Okay, it can be outside as well, as we have seen in this particular case, and here it's not even in the center. So in all these cases, basically the definition is that the spectrum of the signal has frequency components in the vicinity or in the neighborhood of some high frequency f0. Okay, so these are all valid representations of a bandpass signal spectrum. So I just stated it here that the central frequency need not be at the center or even inside the signal bandwidth. Okay, so here it's not at the center, and here it's not even inside the signal bandwidth. But generally, for simplicity, we will consider that to be at the center itself. Okay, normally in our discussion, we'll consider it to be at the center. So if we have to represent this definition of bandpass signal mathematically, just as we did for the low pass signal, then we can write it as such. So what we notice is that the spectrum of the bandpass signal is 0 outside the band f0 plus W and f0 minus W. Similarly, on the negative side, outside minus f0 plus W and minus f0 minus W. So we just have to write that mathematically as. So that's the way of writing it. So the spectrum is 0 if the frequency f is greater than f0 plus W. That means if it is greater than this to the right of this point. It is 0 if it is to the left of this particular point, which is f less than f0 minus W. Or on this side, if it is greater than minus f0 plus W, and if it is less than minus f0 minus W. Or we can equally write that as this we can write as f minus f0 is greater than W. This is an equivalent way of saying that f minus f0 is less than minus W, and if f this can be equivalently said as f plus f0 is greater than W, and the last one is an equivalent way of saying as f plus f0 is less than minus W. Now we can combine all these expressions into a single form, okay, as xb of f, the spectrum of the bandpass signal xb of f equal to 0 if the magnitude of f minus f0 is greater than W. Okay, and that is what we mean by all these relationships. Anything where f minus f0 magnitude is greater than this term W, then we will have the spectrum as 0, so outside these bands. Okay, the spectrum is defined only within these bands of within a separation of W from the central frequency f0. So that's the mathematical way of saying that what are the frequency components present in the band pass signal. Okay, the next definition within band pass that we are going to see is what is called as a narrowband band pass signal. Narrowband band pass signal, what we mean is that the bandwidth, okay, or the one-sided width here, which is W, that should be small compared to the central frequency f0. So if this value W, that is the amount of spread from the central frequency, is small compared to the central frequency itself, then such a signal is called as a narrowband bandpass signal, or we simply call it as a narrowband signal. Okay, so that's the definition for the narrowband bandpass signal. So basically, we say that the spread from the central frequency, the value W, is much smaller than the central frequency itself, or equivalently F0 is larger than W. In such a case, the bandpass signal is said to be a narrowband bandpass signal. Go from a low pass signal, or if you had to translate a low pass signal to a band pass signal, we would do a frequency translation that we saw earlier. Okay, that is the modulation property. We would exploit the modulation property of the Fourier transform. That is, we will take a low pass signal x of t and multiply it with some cosine 2 pi f naught t. Then that low pass spectrum will get shifted to f naught, so we'll get a band pass signal. So by using modulation, we can convert a low pass signal to a band pass signal. So we see how to go from low pass to band pass. But coming from band pass to low pass is not such as straightforward. It involves some steps. Okay, so for example, low pass to band pass representation. So if you had to write that, so that's basically we want to convert a low pass signal, which we'll call XL of t, into a band pass signal, which will denote as XB of t. How can we do that? We can obtain the band pass signal XB of t by multiplying the low pass signal XL of t with a carrier signal cosine 2 pi f naught t, where f naught is some high frequency value. So with some high frequency value f naught, so we will choose this f naught to be some high value, and when you multiply this low pass signal with a carrier signal of some high frequency, we will get the band pass signal, and that uses or utilizes the modulation property of Fourier transform, which produces frequency translation. And again, because this is a real carrier signal, the spectrum will be two-sided. If it was a complex carrier signal, e power j 2 pi f naught t, multiplying this, then we'll end up getting a single-sided spectrum. So since our cosine 2 pi f naught t is a real signal, its spectrum is two-sided, and therefore multiplying this low pass signal with a real signal will produce a band pass signal, which is also two-sided. Okay, and that is what we have stated here. Okay, because cosine 2 pi f naught t is a real signal, its spectrum is two-sided, and therefore the spectrum xb of f that we will obtain for xb of t by multiplying the low pass signal with cosine 2 pi f naught t, that spectrum xb of f will also be two-sided. Now if you wanted only a one-sided spectrum for the band pass signal, then we'll have to multiply it with a complex carrier signal so if xb of t is equal to xl of t into e power j 2 pi f naught t. So now we have used a complex signal for the carrier rather than cosine 2 pi f naught t, which is a real signal. So in this case, what happens is the spectrum of e power j 2 pi f naught t, which is a complex signal, is one-sided. So therefore, the corresponding spectrum of xb of t will also be one-sided. Okay, so we'll write that since e power j 2 pi f naught t is a complex signal. Complex means it has a real part and an imaginary part with one-sided spectrum. The spectrum of the corresponding baseband signal, which is produced by multiplying with the complex carrier. So the spectrum xb of f, the spectrum xb of f of xb of t equals xl of t into e power j 2 pi f naught t will also be one-sided. Okay, so and whenever we have a two-sided spectrum, as we've seen earlier, for a two-sided spectrum, whatever is the magnitude, that will get divided half on the positive frequency side and half on the negative frequency side. But if it is a one-sided spectrum, all the magnitude will come to the positive frequency side only, because there is no negative frequency component in the one-sided spectrum. Okay, I'll stop here for now, and I will continue with the next step, which is the reverse process. So we have seen here how to convert a low pass signal into a band pass signal, how to go from low pass to band pass. We simply multiply it with a carrier of some high frequency f naught. But how to go from band pass to low pass, that's what we are going to see. So here we have seen how to convert transform from low pass signal to a band pass signal. We will see the reverse process, how to convert a band pass signal and obtain a low pass equivalent representation for the band pass signal. So xb of t to xl of t, and that is what we will see in the next lecture.